Now we're going to have two talks on Supernovae 1AX. The first one by, I have really no clue how to pronounce your name, Saurabh, and the second name? John. Saurabh John. Okay, you learn something every day. Okay, please go ahead.
Okay, well, thank you. I have to also thank the organizers, especially for whoever the decision was to hold the conference in this wonderful place. This was a very nice conference that has turned into an amazing conference, I think, because of the location. So thank you, whoever decided that. So I'm going to tell you about type 1AX supernovae. This is work with my former student, Curtis McCulley, our close collaborator, Ryan Foley, and Max Scherzinger is in the room, and other people who are not in the room, so I don't have to put their names on the slide. But before, I wanted to do just a little bit of a historical prelude. So I've worked with Mark and Nick since essentially the beginning of my research career. Here are two papers from 1998, which were pretty important papers. I wanted to highlight this second one with the High Z team, where we actually looked at what we called alpha, but today we call W. These were weird ideas even in 1998, but we wrote a paper on it. One other weird thing we did was take the available ground-based CMB data, so pre-WMAP. There was hints of a first peak in the CMB, and that was good enough for us. And this was when I was sort of young and foolish, but Mark and Nick were the people who had said, go for it. And we took the hints from the CMB, combined it with our 10 high redshift supernovae, and the low redshift supernovae from the Galactic survey. We got these cosmological constraints, which have held up pretty well. The errors have gotten smaller with time, but this was pretty exciting. So that was obviously a very fun time. The somewhat sad part was that the high point of my research career was my second year in graduate school, and it's been downhill ever since then. But at least when you go downhill, you can enjoy the ride. So, and on that way down, there was another paper which is actually related to what I'll talk about that Mark led on 2005 HK. So who's this person? Hope you recognize him, but just in the style of his talk, I wanted to put up a quote, which he said a few days ago. Someone smart and young will sweep away these silly subclasses, and I'm about to give you a whole talk about these silly subclasses. But Nick was on my thesis committee, and he wrote the referee report for my first author paper, even though we were collaborating and competing on pen. But thank you very much to Nick and Mark, who continue to help me to this day. In fact, as of last week, Mark was helping me out with stuff, so I owe a lot to them. Okay, so I'll talk about type 1AX supernovae. So these originally came from a paper that Weidong Li wrote, identifying supernova 2002CX as what he called the most peculiar type 1A supernova. We've removed that designation now because there are actually quite a lot that are like 2002CX, over 50 objects that are very similar. And so in 2006, I wrote a paper calling them instead, when we started identifying a few of them, that there was an O2CX-like subclass of type 1As. But as we studied them more and more, we really thought these are different. These are somehow different than type 1As. Maybe they deserve their own class and not a subclass. Somehow I don't think that's the sweeping away of subclasses that Nick meant to start another class, but some people don't like this, so if you prefer O2CX-like subclass, that's fine, but then don't cite Ryan's papers like mine. Here are a bunch of light curves, and here's a Phillips relation, I'm happy to call it that, for normal supernovae and then these type 1AXs. You can see that they're generally fainter than you would expect for their decliner. But they're kind of a little bit all over this. And they span a wide range of luminosity. Okay, I want to emphasize that these are white dwarf supernovae, and I really like that term. That's the term I use instead of assuming that all white dwarf supernovae or all thermonuclear supernovae are normal 1As. There is a diversity of things under that umbrella of white dwarf supernovae. But the evidence, if you compare in red, green, and blue are members of this 1AX class. If you compare them to normal type 1As in black, you can see at early times they look very similar. And the only subtle differences are that the velocities of the 1Xs are half the normal 1As, maybe a little bit less, so between sort of 3 and 5,000 kilometers per second expansion velocities. They do have that sulfur line that I think it was Eddie earlier said we thought was a hallmark of a thermonuclear white dwarf explosion. But as you go to later times, they diverge a lot, and I'll talk more about the late time behavior of these objects. Some really nice work that Max led showing, again, that these are white dwarf supernovae. You see all of this in the near IR spectra, you see all of these cobalt lines in these 1AXs, just like you do for normal 1As. So I'm pretty convinced that these are explosions of white dwarfs, but maybe there's still some models that can do these without white dwarf explosions to get spectra that look so similar to normal 1As. Okay. Where they differ in one place is their environment. So almost all, I think all but one of these 1AXs have gone off in pretty heavily star-forming environments. So here's some examples. If you plot up a cumulative distribution, this is a paper, it was a pretty, one of the earlier attempts to do this, but the results have held up pretty well. If you plot the cumulative distribution by galaxy type, you can see these O2CX lights, the 1AXs, follow pretty close to sort of type 2s, for instance. Okay? So this might, suggest you or point you towards a massive star origin for these objects. But I do want to note, for instance, 91T-like 1As also follow this kind of distribution. So I don't think this settles the issue and says they have to be massive stars. I think white dwarf explosions are still perfectly consistent. Obviously, they have to be a young population. Okay. So I'll talk a little bit about progenitors. So here are the pre-explosion limits for normal 1As. So the two best limits are from the two recent normal 1As that we've had, 11Fe and 14J. And if you make a similar plot for type 1A X's, previously the best limit was way up here, 2008 GE. But nature was very kind to us and gave us 2012 Z, for which we had pre-explosion images taken very deep because it was the galaxy, which I'll show you in a second, actually hosted a normal type 1A, which then Adam Racing collaborators for the SHIZ project, I was one of the collaborators, imaged to get Cepheids. So we had very, very deep HST images at the location of 12Z, and the 3 sigma depth we could get to for 12Z is actually minus 3.5. And in fact, it's the third deepest limit. So the only, for all white dwarf supernovae, these are the best progenitor limits that you have. Okay? So when we, saw these data, of course, we thought, okay, well, let's go look to see what we're going to see there. And we expected, just like for 11Fe or 14J, that we would see nothing. Okay? But again, nature is very, very kind to us. At the position of 12Z, here's the supernova taken into HST to get its precise position. Here's the pre-explosion image, very deep. You can see that as a source set, which we imaginatively called S1. So this is the first time that anyone has ever seen a progenitor system at the location of a white dwarf supernova. Okay? And it's in this weirdo type 1A class. So if you look at the paper, we went through we put on Nature, lots of text of trying to figure out what this could be, and there are a lot of things in that region, but we kind of ruled things out for one reason or the other, and our favored model was this blue region. That what we were seeing was a helium star companion to a white dwarf that exploded. And in fact, this model was we already had suggested this model in this paper for these objects to help explain some of the type 1X properties I'll talk about, and their environments. For instance, the helium star plus CO white dwarf channel is the one that produces the most quick explosions. You can have the helium have stable mass transfer at a much higher rate, 10 to the minus 5 solar masses per year. So you can build up that mass under the white dwarf actually quite quickly. So the youngest, and those helium stars are also the most massive companions. So that channel gets you the youngest white dwarf explosions. So one example is in this paper. You take a 7 solar mass and a 4 solar mass closed binary. The 7 solar mass turns into the CO white dwarf. It dumps most of its material onto the other star, which ends up, there's a common envelope that ejects the hydrogen. You get a 2 solar mass helium star, and then when that helium star starts to puff up, maybe on its way to becoming a helium giant, it starts to transfer mass back onto the white dwarf. This can happen very rapidly, and you can build up close to the Turner sacral mass that way. So here's that scenario. And there's a nice analog in our own galaxy. B445 Up was a helium nova. It was a nova where it seems that the accreted material was helium. And so one possible connection is that in that case you had a lower accretion rate of this helium and you got a nova, and then maybe in this 1AX class you get a high accretion rate and you can get to a depth accretion. Okay. So type 1AXs, I mentioned they diverge from normal 1As. They actually diverge from every other kind of supernova in that at late times, they never become nebular. They're still permitted, optically thick lines of iron at very late times, hundreds of days after the explosion, with quite low line widths. Okay? Much less than the escape velocity from the surface of a white dwarf, in fact. And so that, to us, suggested that maybe some of the material was just barely unbound. And so maybe that meant that the whole white dwarf did not disrupt. There's other evidence for high density at late times, again, suggesting that you have this maybe optically thick wind that's being driven by this bound remnant. And there are a couple posters about similar things and find similar results. So people made models of this, and so in fact, these are the models that people had in their computers but didn't publish because they didn't actually completely blow up. But we asked people to look more at them. And indeed, you can have these weaker explosions where you're left with a bound remnant. In this case, for example, this model, 1 solar mass was in the bound remnant, about 0.4 solar masses was ejected. And those kinds of models where you have a lot of trapping of the radiation, some of the nickel that's in the bound remnant, that energy gets trapped and released over a nice long time. You follow the cobalt decay, and that does seem to match some of the observations. So that's what we were trying to test with 12Z. So this is some new data we got in January. So we observed 12Z in January of 2016 to see what happened to the supernova. And we expected that if we extrapolate the supernova flux, it would be well below the progenitor flux at that time. So actually one of the models said that the star that we saw might have been the star that actually blew up. And so if that was the case, it shouldn't be there anymore. Well, I'm happy to tell you that it is still there. The flux is actually a little bit brighter than the progenitor limit, so those are these lines across in BB and I. Okay? And so we think our scenario still seems to work. The big question we have now is it's a little bit brighter than that. So what is the source of the excess flux? Is it the companion was impacted by the ejecta? We'll talk about that. Is it emission from the wind, this photosphere, this optically thick wind? Is it emission directly from the bound remnant itself? Or is there some other source in the supernova ejecta that's confusing things? So we're trying to sort through those possibilities, but so far the model seems to work. I'm going to skip this, but there's a recent suggestion for how to get massive white dwarfs a little bit more. Okay, so my conclusions. I would just want to impress upon you that white dwarf supernovae encompass more than just normal type 1As. So you should think about, for massive star supernovae, that there's a whole zoo of thermonuclear white dwarf supernovae. In 12Z, we actually detected the progenitor system. And the late time HST observation is still consistent with this picture. And I would suggest to you we actually have a very good model for type 1AX supernovae. A carbon-oxygen white dwarf, or maybe one of these hybrid carbon-oxygen neon white dwarfs. They're creating helium from a helium star companion. You get a pure deflagration explosion as the white dwarf approaches the Chandrasekhar mass without complete disruption. You have supernova ejecta and a bound remnant, which drives an optically thick wind. You can get some diversity by how much is left in the remnant and how much is in the wind. Okay? And so that is kind of like a target model. And I would suggest that that target model, which seems to be mostly consistent with the observations, there may be still some holes and we're going to keep trying to test it. I would suggest that that model is actually much more constrained than the model that we have for normal 1As. So instead of calling this, I would say, a silly subclass or these just peculiar weird objects, these might be telling us something very interesting about how normal 1As work or the variety of mechanisms that are needed for normal 1As. So with that,
thank you for this very nice talk. We have time for one quick question. Over there.
First of all, I'm very jealous that you probably found a surviving companion post-exploding. Other people have not been that lucky. But my second question is for V445 hub. I think there's pre-exploding imagery, right, for V445.
Yeah.
Do the colors match to what you find for 12Z?
Yeah, that was on there. I'm not good with the pointer, so let's see. There's V445 hub. So it's a little to the right of where the helium star region is, but it's sort of so that's the pre-nova photometry.
Yeah. Thanks.
Okay, I think we have to move on, otherwise we're not going to have our conference picture. Thank you again.